And here we are once again. It's the physics video lecture. Physics 4B, video lecture 13. Let's begin. Had a lot of questions about the most recent homework assignment. So I'll go ahead and write down what we had here. We're looking at chapter 22. And the problems, pretty much the whole set, 20, 34, 43, 20, 34, 43, 74, and 80. So let's just go through these one at a time. Problem 20, we had that ring of charge. So we had a charge distribution, X, Y, Z, the ring of charge of radius A, charge Q on it, and the E field along the Z axis. So out here at Z, E was equal to K, Q, Z over Z squared plus A squared to the 3/2 power. Is that it? Yeah. So if you graph this thing, say now we'll say E is a function of Z, like this is this E sub Z along the Z axis. Then you'll see it, for small z, it grows linearly, okay. And actually, the negative axis, it's gonna do the same thing. It's going to grow linearly, but it's going to reach a maximum because eventually z squared to the 3/2, which is z cubed, is going to win out over this, and you end up with the 1 over z squared behavior far out there. And this is going to be inverted like that. So we're looking for this point right here, and apparently it'll be symmetric or anti-symmetric. And if we take the derivative with respect to z and set it equal to 0, we'll have kq. So we'll set it equal to 0, and first we'll take the derivative. We'll have 1 over z squared plus a squared to 3/2. Then we'll have plus z, and then got a minus 3/2. We've got 1 over z squared plus a squared to the 5/2 power, and then the inner derivative gives us another 2 times z. The 2's cancel. So anyway, we have to set this thing to 0, and we'll rationalize the denominator. Common denominator will have z squared plus a squared minus 3z squared equals 0. So gives us 2, bring it to the other side, a over the square root of 2. Z equals plus minus a divided by the square root of 2. And once you have that, you can plug it in and find out this maximum value. So we want to do that. So E maximum value when z equals a over the square root of 2. And then we're back to k, q. Now we plug in a over root 2. We have 1 over a over root 2 squared, which is a over 2 squared, or a squared over 2 plus a squared, so 3/2 a squared to the 3rd power, to the 3/2 power. And then you just have to simplify that. K, Q, A, we've got root 2. We've got root 2 to the 3rd in the denominator here. So root 2 times 2. And then here we've got root of 3 to the third, so root of 3 times 3, this goes away, 2k cubed a, oh, and then we have a cubed, a cubed, k cubed a, 3 root 3. And this cancels, we end up with 1 over a squared. Okay, 1 over a squared. Good enough. So what next? Problem 34, I'll just take them in order. So 34 is interesting because it takes us back to gravity. So here we're just going to do some substitutions. Let me go ahead and remind us. So Gauss's law, that's so powerful, we have E dot d area closed surface, enclosed in that closed surface over epsilon naught. And Coulomb's law, we can say, for Coulomb's law, we have E, for the point charge, it's good enough, is equal to is equal to Q over 4 pi epsilon naught r squared. Okay. So that's what we've been working with. Now this looked just like, and really is just like, Newton's law of gravity. So for Newton gravity, what did we have? We had G equals, now we're just talking about a central mass spherically distributed, or spherical point mass, or central point mass if you want. G, capital G, Newton's gravitational constant, Gm over r squared. Okay. So the thing is, we've got this 1 over r squared law, and if we want to have the analogous Gauss's law for gravity, we really just have to make some substitutions. So you're going to have integral G dot d area, and on the right side, you're going to have area vector here. There is going to be a minus sign because the mass is attracted. So there's actually a minus sign in front of here if you're doing the vector and not just the magnitude. Okay. So you're going to pick up a minus sign, but your substitutions you would make would be to substitute mass for charge. So we'll just say M enclosed. And you know, I have to leave a little room here, actually. So let's leave a little space here. M enclosed. But then we've got this, in place of G, we have this 1 over 4 pi epsilon naught. Okay. And so we have to multiply the 4 pi epsilon naught over, and that'll cancel this one right here, and we'll just end up with the minus 4 pi G. So you can literally just make those substitutions. The minus sign came in from the attraction, and otherwise we just compared, you know, we had a 4 pi epsilon naught here in the denominator that we don't have here, so we just multiplied it over. Okay. So good, that's problem 34. Now let's go back to electricity. Problem 43 was a nice application of Gauss's law. So this time we'll set it up carefully, make sure everything works out right. So for Gauss's law, we can do this. We can say integral, closed integral, surface E dot n hat d area, surface normal, is equal to 1 over epsilon naught, and then the enclosed charge we can say is the integral rho d volume. Okay. And this is the surface that bounds this volume here. So let's see what they gave us. We were given a field oh, here we go. Wrong page. So we're given a density rho of R is equal to B over R for radius, or less than the radius there, and it's 0 outside. So what we're going to do is integrate up all of the charge first. So Q total is going to be the integral of rho d volume over that sphere of radius R. I'll just put R here. So what do we have? The density is B divided by R. The volume element, you do the shell, 4 pi R squared dr 0 to capital R. So that's going to give us our total. And we have 4 times pi times B out front. R squared over R is just R. The integral of that is R squared over 2. 0 to R, so we have R squared over 2, so we end up with 2 pi B R squared. Okay. So that's the total charge, and if we want the charge inside of a volume lowercase r, it's clear we're going to just replace this uppercase by a lowercase r. Okay. Good, so that's the total charge. Let's see what's next. Yes, then we want E outside, that is to say, let's say, find E for R greater than capital R, E for R less than capital R, right? Capital R is the radius of our object. Well, the thing is, this one we already have, because we did it before. If you're outside of the object, it's just Q enclosed total divided by 4 pi epsilon naught R squared. So we're going to have, for this one, E is equal to 1 over epsilon naught. Actually, Q total over 4 pi epsilon naught R squared. This is one we've done. 4 pi epsilon naught R squared. Because once you're outside, it's just like a point charge, spherical charge distribution. But we can go ahead and plug this in, so we'll have 2 pi B R squared over 4 pi epsilon naught lowercase r squared, and we end up with B R squared, what do we have, 2 epsilon naught lowercase r squared. So that's the one. Now inside, we'll use the formula up top again. In fact, we'll write it down, so this one here, E for R less than R. If we use this formula here, spherical symmetry, we just have E times 4 pi r squared. Field times surface area, okay? On the right side, we have 1 over epsilon naught, and now this integral taken out to the same r, okay? Taken out to the same r. You know, the picture that goes with this is now where this is radius r, now we're somewhere inside at lowercase r, okay? That's the picture, Gaussian surface. So this integral here, which we've done, and which is clearly, if we go out, you know, if we have an r prime, dr prime, we go out to lowercase r, it's just going to be lowercase r squared. Okay, so we'll have 2 pi b lowercase r squared. And now things are different, right? We're going to be able to cancel pi r squared, and we'll have, get rid of the 2 here, we'll have a 2 up there, and we will get E equals B over 2 epsilon naught. Okay, now how does that match up with this one right here? This is a constant, okay? Let's go ahead and do the graph. This is E, this is the radius r. We now have this constant value out to here. And you'll notice we get the continuity because when lowercase r equals uppercase r, you get a 1 there, b over 2 epsilon naught, same as there. So there you have it. Okay, that was problem 43. Now we have 74 and 80. Problem 74 and 80. Okay, so for problem 74, we have our loop of charged loop of radius A. Okay, here's a z-axis. So once again, these positive z up, negative z down. We have E was equal to K, Q, Z over Z squared plus A squared to the 3/2 power. So now what they told us to do was suspend a charge Q here, or a mass that has a charge Q there. And the idea is we've got gravity pointing down, and we have an attractive force because we're going to have opposite sign charge. So one of these is negative, one of them is positive. Let's see what we have here. Yeah, this is a negative Q. So I can put a negative sign here, negative Q. Okay. Let's make that a little neater. So K, negative Q, Z. So the force, if you have a positive charge here, is going to be attractive. There's going to be an electrical force and an mg pulling down. So the net force is going to be K negative Q, Q, Z, Z squared plus A squared to the 3/2 minus mg, like that. And because we saw earlier, this force gets weak if you go too far away. There's going to, for a given weight, there's going to be a point at which the electric field can't hold it up anymore. On the other hand, if you're close enough and you have the right mass, the electric field can hold you up against the force of gravity. So that's the idea there. And the limiting case will be when F net is equal to 0 when you're at that maximum. Okay. So if you have the Z equals, if you have that Z equals root A over root 2, that's that maximum value, and then you have your Q over M, and it has to be equal to G. So, or it's equilibrium K negative Q, minus A over root 2, that's for the Z, minus A over root 2 squared plus A squared to the 3/2. That's where that maximum was that we just calculated, equals mg. So to find the minimum Q over M, you put the Q over M here. I could do that. In fact, let's put this out here. We'll do a Q over M G. So we'll divide by G and divide by M. And we've got Q over M here, because that's that thing, equals 1. Okay. So that you cross multiply, and that defines this minimum Q over M, because if it's smaller than that, which is to say this ratio, mass could be too large for the thing to hold it up. These minus signs cancel, you see. Beyond this, though, it's not that interesting. It just gets into algebraic difficulties. But this defines, I'll just write here, solve for Q over M, and then you're done. Okay. Then they said if you have twice that charge, well, it's no longer going to be at that max, it'll be up somewhere higher, but the algebra doesn't look so good. Okay, be that as it may, let's declare victory on this one like that. Problem 80 is again this ring of charge, and this one is of more interest. So this time we're going to have this same ring and a charged particle close to the origin. So let's draw this. Now they used X and I used Z, but it shouldn't matter. X, Y, Z. So we're just going to write this same formula here. E is equal to K Q X over X squared plus A squared to the 3/2. And once again, let's go ahead and draw the graph. This time we need both sides, but we'll make it a little smaller. Okay, so that's the E field. If it's if it's a positive charge, it's pointing away in both directions. I forgot to put the ring here. Okay, there's the ring. And again, we know that it has this form here. So now if you're close to the origin. I'll put some brackets here, okay? So you're close to the origin, you're within that linear regime. Then if you put a negative charge here, then you're going to get a minus sign in your force, and you're going to have a restoring force. So, force on negative charge minus Q. So that way Q's a positive number minus charge. So we have F is equal to minus K Q Q X over X squared plus A squared 3 halves, okay? If X is small enough, this is a restoring force, okay? If X is small enough, we have a restoring force. So that my square red brackets indicate that we have a small zone in which we're on this straight line part here. That's the idea. Okay. So now here's something that we did the other day. We're going to take f of x approximately equal to f of 0 plus f prime of 0 times x. That's just, it's either the first two terms of Taylor expansion around 0, or you can just take that as the definition of the approximation using a, we did this last time, so we could say delta f is equal to f prime delta x, that kind of approximation. But we're going to go ahead and use this right here. So let's do this expansion. What we're going to do is do the expansion. We're going to find a linear force law, and then we'll get an oscillation of a charged particle basically back and forth along the x-axis between the ring there. That is the plan. Let's go ahead and make up a little, free up some board here. Yeah, oscillating charges are important, play a big role. So this is an interesting problem. So what do we have here? F of 0 is 0, right? Just plug x equals 0 in. Let's get f prime of x. F prime of x, we've got k product of the charges. It's got a minus sign there. We have 1 over x squared plus a squared to the 3 halves. And then we have plus x, negative 3 halves, 1 over x squared plus a squared. 5 halves, the inner derivative gives us 2x times 2x. Well, we're going to evaluate it at 0. So this is going to go away. We've got x and x at 0, x squared at 0. But this part we keep, so f prime of x is equal to minus k q. Got a 1 here, and in the denominator we have a squared to the 3 halves power, so a over a cubed. Okay. That's our derivative. Now we'll do Newton's law. Now, Newton mass times second derivative with respect to time is equal to force. Mass times acceleration equals force. Here, we have mass times acceleration. This is from your oscillations chapter in Physics 4a. Is equal to the force, f prime of 0. Got that? So it's equal to the force. So f approximately f prime of 0 x is equal to minus k q q. that was the continuation of this discussion. Now let's plug it into Newton's law. Minus KQQ over AQX. And that's the differential equation of the harmonic oscillator. So look that up, because once you have mass second derivative with respect to time minus constant times x, you can immediately declare your angular frequency is this quantity divided by m. So K, Q, Q, M, A, Q. So there's your frequency. And yeah, the situation is we've got a stable equilibrium to the linear force law, and we get harmonic oscillations. Okay, good. How long did that all take? Okay. Let's move on. I'll erase all of this. So we're moving into a new chapter. New chapter, potential and potential energy. And it builds really nicely on the electric field concept. There are some nice simplifications coming up. So we'll call this chapter Electrical Potential. And I'm going to start with potential energy in mechanics. So in mechanics, potential energy, you can write U is equal to minus integral of F vector dot dl, and we're going to start with a delta U. So that's a change of potential energy if you integrate from 2 points in space A to B. So this is a line integral. And I'm just going to immediately go to the, I'll explain more of this when I transform this to the electrical version, right? So this was the general version. We learned about it in mechanics. So potential energy in this form. So now we have the same thing. You know, we have a force law. Okay. We'll do the same thing. Integral A to B. But what is our force? Q times E dot dl. Still a line integral, formally the same, except we've got that charge right there, that electric field. So still a line integral. And this is joules, right? The unit here is joules, energy. And what we can also do here, so this is change of potential energy. We can introduce something called the potential simply by dividing by this Q. Okay, let me go ahead and put a little subscript here. Think of it as a test charge. And we have delta V is equal to delta U divided by Q naught is equal to this line integral minus sine a to b E dot dl. So really the fundamental object we need to work with a bit is this line integral along the electric field, or through the electric field in space. I'll put a box around this. We can talk about the units already right away, because force times length is work, is energy. This, of course, was also energy, because Q times Z is a force. So what are the units here? Units. We have the units of this delta V are joules per coulomb. Joules per coulomb. That's the volt. Joules per coulomb. That's energy per charge. So that's our volt. We already know we have newtons per coulomb for the electric field itself. Okay, now we have to say something about these line integrals. This is a dot product. Okay, so E dot dl, and the dl is along some curve in space. So suppose you have a point in space. These are actually points in space, so vector A and B. You got a point in space, you've got a curve, goes out to B. Okay. So this integral A to B would be along here, and our elements dl, if you construct them as infinitesimals, all these little segments, you can actually build Riemann sums the same way you did in calculus. Okay. Yeah, so that's our dl everywhere. And then the field is a vector that's being multiplied with that at every point. So we could have an E field here, okay, and then E dot dl, I've constructed it to have a 90-degree angle. Okay, that would vanish. Okay. On the other hand, over here, if you had E dot dl, these would be almost anti-parallel. You'd be almost looking at a factor of -1 times those two lengths. Okay, so just a scalar product, and you add them all up, and you've got an integral. Now we're not going to do some random curve here, because what we're going to find is it's just going to depend on the end values of this potential at the end points. Okay. It's actually going to be independent of what curve we take between a couple of endpoints, so that's going to be powerful. Two examples though. Suppose you have the E field of a point charge. Okay. So we know it's radially outward, and suppose our curve is just along a circular arc. Okay. So if our curve's along a circular arc, every time we cross an E field line, we've got a 90-degree angle. And that change of potential will vanish. Okay. So that's going to be an important example. So I'll just write here, delta V equals 0, because E dot dl is equal to 0 the whole way around. And the other example, here I'll put it over here a bit closer. The other example is just as easy. That's if your DL and your E are parallel or anti-parallel. Okay. If DL and E parallel, then what do we get for our delta V? Okay. We just get minus E dot, all right, delta L, like that, okay? So those two easy cases where the change is 0 and where the change is just that linear expression, those are the two basic examples. Let me check the clock. Okay, the way I'm gonna build it up this time is to go straight to the point charge, okay? Because the point charge was our fundamental charge. We're gonna go for the potential energy and the potential, in particular, the potential of a point charge, and from there we'll build things up again. So now we're going to talk about electrical potential of a point charge. So here's our point charge, Q. Could be positive, let's let it be positive. Okay. We know that the electric field is KQ over R squared directed radially outward, which is the unit vector R hat. Right? So we know we've got these radially outward point charges. We're going to construct this delta V. I'm going to write V. I'll just write delta V for starters. Okay, delta V minus integral, and now we have to have the KQ over R squared, R hat, and then our DL. Okay. But the nice thing about this R hat business here is unless DL is pointing radially outward, the contribution is 0. Okay. So this turns into, let's go ahead and write A to B. This turns into minus KQ integral this just turns into dr scalar, right? Scalar product is a scalar, only dr, the radial component, matters. So we have dr over r squared, got a minus sign. Now I'll write r sub a to r sub b minus kq. Minus 1 over r sub a, r sub b equals kq over r sub b minus kq over r sub a. And what we do now, this is the formalism for potentials, is we let our beginning point be out at infinity. Okay. R sub a goes to infinity, this goes to 0, and we have delta V is equal to V minus, I'm going to write V infinity is equal to V, because this one is 0, is equal to KQ over R. So this is what we're left with. there's our formalism. The potential, electrical potential for a point charge, KQ divided by R. Point charge, obviously, point charge at the origin. Potential of point charge at the origin. So this is the fundamental unit that we're going to make use of. Yeah, this replacement is really key. You're either, you can make this DL into a radially outward and a perpendicular component, and the perpendicular component dotted into R hat vanishes, so that just turns into dr. So this was all fair and square, and good. We have a potential energy, we have a potential, now we also have a potential energy. So now suppose we have, now consider 2 point charges. Q and Q prime. So here's Q. Here's Q prime, and they're separated by a distance R. We just reverse our definition. Remember, we got the delta V by dividing potential energy by Q. So now, potential energy U is equal to K Q Q prime divided by the separation distance. So now we have potential energy, and we can actually do really interesting things, namely motion due to kinetic energy and potential energy and energy conservation. But yeah, so that's the potential energy, these 2 point charges separated by R. And yeah, one of them's at the origin, okay? We're gonna generalize that eventually, but we've got charge at the origin, we brought another one. If you want the potential energy of a collection of charges, potential energy of 3 charges, say you had these 2 charges, and you brought a third one in, then charge 1, 2, and 3, R1, 2, R1, 3, and R2, 3, those would be their respective separation distances. You would just add up a bunch of these expressions here. So U total would be the sum of these individual ones, the individual potential energies. I'll just say U sub I. And in fact, this triangular configuration would start out with one of these expressions like this. You brought in that third charge, you would get a potential energy from here, these 2, and a potential energy from those 2. So for small collections of charges, you just add them up, add up a bunch of these. Once you get more than a few, though, you're going to want to start doing integrals, which we'll do as well. Okay, so far so good. Must consult the clock once more. Okay, perfect. And yeah, I'm just sketching a couple of points here. So 3 charges or more charges, you add them up. Then you have conservation of energy. So without any complicated integrations, you just have these very simple formulas here. You could say, cut the bonds between all three of them, they'd zip out to infinity, you could calculate their speeds. Okay. So that's going to play a really interesting role. Good, let's do an example here. The thing to note, when we sum expressions like this up, and I'll do it explicitly, that's a little vague, we're not having to do integrals anymore. We're just adding some numbers, putting some distances in there, and the information is there still. Okay, good. Let me go ahead and give this example. So, potential energy, so let's call this point charges, potential energy, and energy conservation. Because we know kinetic energy plus potential energy is conserved. So my example, to show how this works, let's say we have Q1, I'm just going to have MQ, we're going to start with the simplest example. So these two masses with charge, point masses with charge, equal mass, equal charge, are separated by a distance r. Okay. So E is equal to K Q squared over R. Right? K Q prime over R. So that's, and let's even call this R0. That's the total energy initially. Now what happens if we were somehow able to break the bond here and they just repel each other and fly out to infinity? Okay. So if particles are released, then you know we have kinetic energy plus potential energy is equal to E, which is a constant, and right underneath there you would say, you know, 1/2 mv squared plus k q squared over r is equal to k q squared over R0, because that was their initial energy. Okay, kinetic plus potential is an energy. Well, did I release one of them or both of them? If one of them is nailed down and one of them flies away, then I have 1/2 mv squared. If both of them fly away in opposite directions, I would have 2. Right? So if the particle, so we have to say if particles are released and fly apart, then we would have to multiply this by 2 for the 2 masses. And we could do this for a collection of masses as well, or we could say one particle is nailed down and the other one flies away or approaches. It's all very basic conservation of energy. We're going to use this to talk about the Rutherford experiment later. This basic calculation here. Good, so there's that. Let's see what else I have to introduce here before I put a homework up. Thought I had a homework assignment for you. Yeah. Let me consult the assignment right away. Consulting the clock. Okay, yeah, so this is for charged particles in motion. Actually, at rest and in motion. Okay, you just write this equation down, you can solve for one unknown. In fact, let's continue this thing. Suppose the particles go out to infinity. How fast are they moving when they are very far apart? Then then this one goes away and we just have this right here. So then V final, 2's canceled on the left, is equal to K Q squared over R0. That was V final squared. M square root. Okay. That would be that easy. Okay, so that's for collections of point charges. Let me go ahead and go to the potential of a continuous charge distribution. I'm going to do that right away. Point charges, you just add as many of these up as you need to. Okay. At some point it gets a little tedious. Okay. Up to 3, maybe 4 charges, you can still do okay with that. So let's wrap it up with potential of continuous charge distributions. Continuous distributions of charge. And we'll start with this. We know we have V equals K Q over R. And in fact, let's put the sum there. Sum of K Q over R. And we're going to turn that into an integration. The K comes out, we're integrating dq over R. But now we have to specify a bit. Okay, this is just very loose. V of position R is going to be equal to K integral dq. I'm going to write of R prime, and this distance, right, from the charge to my point where I'm measuring the potential has to be taken as the magnitude of R minus R prime. So what you're doing is you're integrating over the R primes, and this is your distance here. The example I want to have is from the homework right away. Example from the homework, let me consult the text here. We're looking at problem 51. This is a good one. Y-axis, x-axis. Good. So for the homework we have a y-axis, no, other way around. Y-axis here, x-axis here, and we've got a charged rod distributed like this. So I think it's going to be minus L over 2 to plus L over 2, yeah. So it's got total Q and L over 2 minus L over 2. And we want the potential at some point x on the x-axis. So what we're adding up is a bunch of elements of dq on this y-axis, and the distance is always this hypotenuse here. Okay. And this hypotenuse is root x squared plus y squared, and we're integrating over dy. So what would our v be? Am I doing this for you guys? We would have a v of x, got a k. The integral is going to be minus L over 2 to L over 2. And this dq is going to be q over L dy. Okay. And you're going to have the root x squared plus y squared. So you're integrating over y. Okay. So x is your variable. You may have to look this one up in integral tables, see what you find, okay? It's well defined, L over 2 to plus L over 2. And the problem asks you to consider the case when x is large. It's going to be really, really interesting because same as our old symmetry considerations, when you're out here far enough on x, this thing looks like a point. When it looks like a point, it's supposed to just turn into kq over x again. So you'll see how that works. That's a good problem. Let's go ahead and leave it at that, and we'll put the homework assignment up. Oh, I have to mention one more thing. Because of what we learned already about the spherical symmetry, if you have a spherically symmetric charge distribution and you're outside of it, it's got the potential of a point charge. Just like you have the field of a point charge if you're outside of it, you also have the potential of a point charge for a spherically symmetric distribution. Okay, you guys put that in words while I write up the homework assignment. This is for, this is number 13, right? Chapter 23, problems. I just had 2. We'll get more of them next time. The 2 problems were 23 and 51. 23 and 51 of chapter 23. Good. See you guys next time.